we can handle one inductor or one capacitor in a circuit and do first order transient analysis. What happens when we have 13 capacitors and 6 inductors and sinusoidal voltage and current sources? That's what we do this week. It's the last piece of the jigsaw, if you like. Sinusoidal inputs are important, not just DC. We know that's how power's distributed. Analysing circuits with sinusoidal inputs is important. And it turns out that even if we have lots of capacitors and lots of inductors, with a little bit of a magic trick, all of the circuit analysis techniques we've used so far, certainly KCL, KVL, they apply, nodal analysis, mesh analysis, we can just do it all again, even though we've got capacitors and inductors and sinusoidal sources. The magic trick is going to be that voltages and currents will be complex numbers. Why might that be the case? Well, think about it. If you've got sinusoidal sources, how do you specify a sinusoid? Well, it's amplitude and its phase as well as its frequency. It'll turn out that the frequency doesn't matter, it's the same everywhere, so that we have to keep track of amplitude and phase of currents and voltages. What's a simple way to keep track of an amplitude and a phase? A complex number. Essentially what it gives us, an amplitude and a phase. So that's what we're leading to this week. Everything, we can do all of these circuit analysis techniques, Thevenin, you name it, but we'll be dealing with complex quantities. Resistance was real. We're going to move to something called impedance, which is complex. So that inductors, capacitors, resistors can be all treated in essentially the same way. And we go back to our standard circuit analysis. So that's the objective. I think that'll be lecture 2 and lecture 3 down the bottom there, not just lecture 2. There was one from last year. I'm still waiting for more for this year. At the moment, there are only 2, and they're both prize winners for this year. So that one was quite good and really captured something, and maybe got the Lecturer's Choice Award. Your melts question. Simple circuit. We've looked at ones like this before when the source was DC, but now the input source is a sinusoid. Some amplitude Vm times cos of omega t. Omega is the angular frequency, how fast it's jiggling up and down. What happens to the voltage across the resistor as the angular frequency omega increases? So I'm interested in this voltage here. What happens to that voltage as the angular frequency increases? I didn't put the answers on there. It's like increases, decreases, stays the same. And another one. So obviously you think things are going to be sinusoids. Other voltages and currents might end up being sinusoids as well. So what I'm interested in, what's the amplitude of the voltage on the resistor? The amplitude of the voltage on the resistor as I increase omega. You can think about how an inductor behaves at low frequencies, or even DC. That's the limit of low frequency. How does an inductor behave at low frequencies? How do you think it behaves at high frequencies? What you know about it is that V equals L times the rate of change of current. V equals L times the rate of change of current. We said we know then what it looks like at direct current or really low frequency. What happens as the frequency increases to an inductor? Does it become sort of like a bigger resistance or a smaller resistance? Okay, let's go 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So roughly speaking, about in terms of what happens to the amplitude of the voltage across the resistor, 20 out of 57 say it decreases, 18 out of 57 say increases, 14 out of 57 says stays the same. Well, I can show you what happens. The special case that Vm was 1 volt, this is 1 ohm, and this is 1 Henry, but it's just as good as anything else in terms of illustrating the general behaviour. The blue line up there is the input voltage, Vm cos omega t, for this particular case, where omega is 1 radian per second. And the red is the output voltage, so the voltage across the resistor. So there are a few things to observe from that. I've solved the differential equation and plotted it in MATLAB. A couple of things to notice. It doesn't quite, it's sort of got this little bit at the start here. What's that? That's some exponential transient. Exactly the same exponential transient with the same time constant that we would have got when the source was DC. That transient doesn't change. Okay, so there's still these exponential transients there. Whereas when we had a DC voltage source, the steady state was a DC value with a sinusoidal driving function. The steady state up here is sinusoidal. So that's the first thing to notice. There is this transient still, but then there's the steady state, which is another sinusoid. And what do you notice about the frequency of those, the red and the blue? It's the same. No, nothing we do in terms of having different resistors, capacitors, inductors can change the frequency of the input. Linear operations don't change frequency. You can differentiate sinusoids, another sinusoid of the same frequency. Multiply it by a scalar, add things together. You can't change the frequency with linear operations. You would need nonlinear operations like diodes to introduce other frequency components. So if we've got one frequency source, everything else, every other voltage and current is going to be the same frequency. And so we can see that there. But what is different is the amplitude. So the red one has a different amplitude, and it has a different phase than the input. And generally, that's what we'll have to keep track of. This has got a different amplitude than that, and it's phase shifted. The maximums aren't occurring at the same time. So steady-state sinusoidal analysis, which is what we're worried about, just involves determining amplitudes and phases all over the place. Amplitudes and phases. How have they been shifted around? So we see a couple of things there. The transient behaviour, we know what the steady state is. We're looking for sinusoids. And in that case, that's what the amplitude is of the red. So that's our output voltage for 1 radian per second. Let's up the frequency. There's 10 radians per second. You can see the voltage on the resistor has dropped considerably. It's down here now. What about at 100 radians per second? Well, 100 radians per second is not really getting through. 1 radian per second through with good gain. Certainly by the time you're at 100, there's only a tiny little ripple there. So the answer was decreases. And why does it happen? Well, at low frequencies, an inductor looks like a short circuit. We see, in fact, at DC, it looks like it is a short circuit. But that means at low frequencies, like 1 radian per second, it essentially is a short circuit. Okay? It's really not doing much. But if you try and change frequency quickly, V equals L times di dt, the voltage on the inductor is going to increase as you increase the frequency. And that means the voltage on the resistor has to decrease. Still got Kirchhoff's voltage law around the loop. Okay, so as you try to increase the frequency, the inductor chokes the current, sometimes called a choke, an inductor. It's not easy to quickly change the current through an inductor. It resists that change. And so that's what we can see happening there. In the limit, the frequency gets high enough, essentially all the voltage is used up trying to change the current through the inductor, and there's nothing dropped across the resistor. This is an example of a low-pass filter. Frequencies are about 1 radian per second get passed, 10 get passed a little bit, but 100 radians per second get ruled out altogether. So if you're interested, you know, it was a speech signal and you wanted to get rid of high-frequency components, just leave a voice signal to go through, that simple circuit would kind of do something. And it only had used one resistor and one inductor to do it. If you want to make fancier ones so that, say, by 10 radians per second you were already zero, you're going to have to put in more capacitors or inductors. And so there's a whole field of filter design, which is about, well, how do I make something that passes these frequencies but blocks these ones? It's called the roll-off, how fast you start, you know, getting rid of frequencies. So this one isn't particularly fast because it only has one element. If you put more elements in the right way, more capacitors and inductors, you can make fancier filters. You could put op-amps in there if you wanted gain as well. If I wanted a gain of 100 at the start instead of the gain of, you know, just below 1, well, I'll just put an op-amp in there to give me some amplification. And as well as that, you can do them digitally. So you don't have to just do them in analog domain. I could go into an analog to digital converter and use those OR gates and AND gates and NOT gates that you saw a while ago and actually do the filtering digitally if you wanted to, or using your computer. Write the filters in software, whatever you like. But this is an analog low-pass filter. That simple thing there is an analog low-pass filter. So how would we analyse that? That's great. We've seen some MATLAB pictures, but where did I get the equation from? Well, we do the same analysis that we did last time. We do Kirchhoff's voltage law around that loop. It's just that instead of there being 6 volts there or some constant, there's Vm cos omega t, and that just changes the solution to the differential equation that we get. It's just another first-order differential equation. Now it's going to have a different solution because we have a different driving function. Okay? But from the circuit analysis perspective, it's Kirchhoff's voltage law around that loop. So I'm going to quickly do that for you, just so you can't say that's me. I'm going to do it with that special case where that was 1 ohm, that was 1 Henry, and that's 1 volt. Okay? Just easier than leaving in R and L and Vm. So I'm not going to do anything to start with that I know you couldn't do, because I'm just going to do Kirchhoff's voltage law around that loop. Well, let's even I'll leave in the V and R and L to start with. You get minus Vm cos omega t. That's just KVL starting here, going up that way. In terms of the current, the voltage drop across the resistor is I times R. And in terms of the current, the voltage across the inductor is L by the derivative of current with respect to time. And that equals 0. Exactly like we did last time, the fact that this is a time-varying sinusoidal input now doesn't change KVL. Therefore, I get di by dt plus 1 on L on Ri equals Vm cos omega t. Only difference, again, is the voltage source. It's not a constant, it's Vm cos omega t. You can see down here the time constant of the transient is L on R, same as we got last time, but we're in fact not so much interested in transient behaviour now. It's what happens when that's died away. What are we left with? Now take the special case where Vm equals 1 and L and R are both 1, just to make it as simple as we can. I get di dt plus I equals cos omega t. And I want to solve that differential equation. Remind myself what it was. Di dt plus I equals cos omega t. Does anyone know what the general solution will be for that? So the general solution it'll have a transient component with time constant 1, so it will have an e to the minus t term. As I said, we're really not that interested in that for our analysis in this lecture. And then if I have a sinusoidal driving function, the steady state solution will be another sinusoid. But it could have a different amplitude and phase, so I can do that by putting A2 cos omega t plus A3 sin omega t. So by taking a weighted combination of cos and sine, I can get a sinusoid with any amplitude and phase I want. And that's all I can get. That is the general solution. I need to solve for the constants A1, A2, and A3. So if that's my proposed I, let's differentiate it. See if you believe this. Well, I get minus A1 e to the minus t. What's the derivative of cos omega t? Negative omega sine omega t, thank you. Minus omega A2 sine omega t, and the derivative of sine omega t is plus omega cos. If I add those two things up, I plus di dt, because that's what I have up there as the left-hand side of the equation, I get, well, the transients a1 e to the minus t and minus a1 e to the minus t, they cancel. And that's always going to happen. That's the transient solution. It's got nothing to do with the driving function. So that's why you always get that transient component no matter what the input voltage source is. So that disappears. I will get A2 cos. So there's an A2 cos and then an omega A3. So A2 plus omega A3 cos omega t plus there's an A3 sine minus omega A2. So an A3 minus omega A2 sine omega t, and that has to equal cos omega t, because that was the right hand side up there. So how do I solve for A2 and A3? I match coefficients of cos and sine. Yep. For that to be true for all t, the only way it can be true is if this equals 1 and this equals 0. Now you can match coefficients of polynomials, or in this case cos and sine. The only way it can be true for all t is if those coefficients match. So I had to solve A2
plus omega A3 equals 1, and minus omega A2 plus A3 equals 0.
Two simultaneous equations in the two unknowns, A2 and A3. I'm sure you can solve that. You will get A2 is 1 on 1 plus omega squared, and A3 is omega on 1 plus omega squared. You say omega, I say omega. So I will equal A1 e to the minus t if I plug them back in, and I don't know about A1 yet, that just disappeared. So what I've done so far doesn't tell me what A1 is. But it's plus 1 on 1 plus omega squared cos omega t plus omega on 1 plus omega squared sine omega t. A1 I can get from an initial condition. So if I wanted to get the complete solution, you told me the initial condition now, what's I0 for example, then I can work out A1. And I would get exactly the solution that I plotted before. There's a little transient with time constant 1, but when that's dead, so let's just be clear, that's transient, it dies away, that's what transient means, and that this, it doesn't die away as time increases, that's the steady state. And that is what we're interested in finding this week. What's all the steady state behaviour when the transients have gone? Now, that's not the form I want it in, because I want it as something cos omega t plus something, so a phase. I want an amplitude and a phase of a sinusoid. I don't know it yet. It's something cos plus something sine. So then your trigonometric identities come into play. So I'm just interested now in the steady state solution. And I can write it in this way. So the steady state solution, say I steady state, equals that. I've just pulled 1 on the square root of 1 plus omega squared out the front. Why did I do that? I'm trying to write this as cos of omega t plus an angle. So perhaps remembering your identities, you'll realise that this is what? Cos of omega t. Does anyone know? What's the angle, the same way of writing that? Cos of omega t minus tan inverse omega. If you want, I'm not teaching basic trigonometry here, teaching circuits, but just so you might remember this little triangle. That angle theta is the one we were after, and you use the identity that cos of A plus B is what? Cos A, cos B minus sine A, sine B. Is this all right? You've certainly done that before. So I can write it in this way. So that's the amplitude and that's the phase. Remembering my input was just cos omega t, and you can see now what happens. The amplitude's changed to 1 on the square root of 1 plus omega squared. That's the amplitude of the current. And the phase is tan inverse omega. So you can go back to those red lines that I had, and that's what I've plotted. what happens to the current as omega increases? 1 on the square root of 1 plus omega squared. It's decreasing. So the current is going down. The inductor is resisting the change of current as the frequency increases. So remembering that the voltage on the resistor is just the current times 1 ohm, you can see what's happening. So I plotted the voltage on the resistor, but in this case it's the same as this current. If the current goes down, the voltage on the resistor is going down. So the things we observed, the frequency didn't change, absolutely nothing changed about the frequency. The amplitude and the phase did change, and so we need to keep track of amplitude and phase around a circuit. Now this one required trigonometry to match coefficients to solve for it. Okay. We're going to show that instead you can use complex arithmetic. You can add and subtract complex numbers around a circuit instead of having to use trigonometric identities. But from the circuit point of view, we needed Kirchhoff's voltage law and the VI equation for an inductor. Then it's solving a first order differential equation and using some trigonometry in this case to get the equation in the form that we wanted. Okay, that was the prelude. We've looked at resistors, inductors, capacitors, voltage sources, current sources, we know that. We've looked at KVL, KCL, Thevenin superposition in DC steady state, and we've done some transient analysis with a single inductor or a single capacitor in the circuit. But what about AC? Well, we mentioned it in one of the first lectures. We haven't really talked about it since. We needed all the basic circuit analysis first. But lots of common AC signals are sinusoids, power distribution, wireless carrier signals, audio synthesizers, radio signals, television broadcast. They're all sent on sinusoids. And power, we know, is sent to all of our homes, distributed to all of our homes as a sinusoidal signal. We could solve linear circuits with sinusoidal inputs, and what we'll know is if the input is a sinusoid, every other voltage and current is going to be a sinusoid and it's going to have the same frequency. And the amplitude and phase could be different, so that's what we need to keep track of. We could solve with differential equations like we've just done, but it's easy to solve with complex numbers. That's assuming you know what a complex number is, and you can add them and multiply them. So that is an assumption that we'll be making for the next week. So brush up on your complex numbers if you're a little bit rusty. If you don't know what a complex number is, panic. This was one from, I think, 2 years ago. Who needs Gangnam Style when you have Op and Op Amp Style? Beautiful work. That led us to create a whole song based on Gangnam Style to summarise the subject. You can find it on YouTube. All right, quick revision on sine waves, just to make sure we know a thing or two about them. So this is a sine wave. Has this form down here in the red box. XM is what? Amplitude. Theta is what? The phase. So we've got XM, the amplitude, theta, the phase. What's omega? It's written just there. So omega is the angular frequency in radians per second. It's related to the frequency f in hertz by omega equals 2 pi f. So the important quantities, the phase, the amplitude, and the frequency. Remember, you've either got the angular frequency in radians per second or 2 pi f. What's the the period t as it related to frequency, 1 on the frequency, which is 2 pi on the angular frequency. So there's the basic parameters of our sinusoidal inputs, the things we're interested in: amplitude, phase, and frequency. Although given the frequency doesn't change, if you have a driving function of a particular frequency, everything else will have the same frequency. We're really interested in amplitudes and phases. Some terminology, though, called leading and lagging. We talk about, in this case, the dashed. Do you think that dashed sinusoid is sort of ahead or behind the other one? It's ahead. It sort of reaches its peak up here a little bit before the red one. So we say the dashed line is leading the red line. And in this case, the dashed line is leading the red line by theta. So because of this plus theta here, we say that the dashed line is leading the red line by theta, or the red line is lagging the dashed line by theta. So you could be leading by theta, lagging by theta. If there's a plus theta there, this one is leading, but you can't read that, leading that one. Okay, what do we get? So omega t plus theta in total is the argument of the sine function. Theta is the phase angle. I've mentioned this thing about leading and lagging. If the phase difference between two sinusoids is 0, we say they're in phase, otherwise they're out of phase. And just something to note, we often write it like this when we do our circuit analysis. We'll put the phase angle in degrees, not in radians, but it shouldn't cause any confusion. But we will often write it as sine omega t plus 90 degrees. You need to know these relationships between sine and cos. In particular, that you can write cos as sine of omega t plus pi on 2, plus 90, and sine omega t is cos of omega t minus pi on 2, or 90. Another thing that's useful, minus sine, you can instead add plus or minus 180 degrees to the phase, if you want to get rid of the negative sign out the front here. So to find the phase difference between two sinusoids, well, you only ask it if they're the same frequency. They must both have positive amplitudes, and they must both be sine or must both be cos. So let's see what that means more concretely in this example. Okay, you've got to determine the frequency of these sinusoids and find the phase angle between the two voltages. Find the phase angle between the two voltages, and that is De Melt's question. I'll just unlock. Should require a little bit of work. What is the phase angle between them? There are the 4 options down there. You might have to use the relationships that were just on the previous slide. Converting cos to sine, getting rid of negative signs out the front. Feel free to chat, make noise. might start it and see how the answers change as I... See if that helps. A few people changing, not quite converging on the right answer yet. That needed to be plus 90. Because sine of something plus 90 is cos of that something. See if that helps. I've got it in form now where they're both positive amplitudes. V1 and V2 are now both in terms of sine. So it's a positive amplitude times sine, the same frequency, and a phase. So now I can directly compare the phases of the two. Okay, that's good. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. So in the end, basically 50 out of 70 said that V1 is leading V2 by 120 degrees, which is the correct answer. V1, now so these two tricks, I got rid of, this wasn't good. It had a negative out the front and it was cos, so I had to fix both of those things up. First I got rid of the negative there, then I got rid of the cos or changed it to sine. Now it's simply a matter of saying, well, this one's plus 60, this one's minus 60, so that V1 must be leading V2 by 120. V1 is leading V2 by 120. I could also say V1 is lagging V2 by 240. Would have been, these things only 360 degrees in phase, and they can slip. So if you're leading by 120, you're lagging by 240. It's essentially the same thing. I would have got that if instead I'd put because I could have put plus or minus there. I could have put plus, and then I might have got this other thing in terms of 240 rather than, and that would have also been fine. You're not doing anything wrong if you get that, but just wasn't one of the answers that I'd had up in this case. Okay, but there would have been, if you did do that, if you put plus there instead of minus, that's fine as well, absolutely. Are there any questions about that? Certainly split the votes early on. It does, I must admit, I do need to cheat occasionally with this leading and lagging and look at my notes. So I understand, and cos, is it cos plus and minus? I need to shift them around in my head. So there are a few little things to remember to get it right. All right, so this we've really mentioned, but I'll quickly go over it. If you apply a constant sinusoidal forcing function to a linear network, where you've only dealt with linear networks apart from diodes, The steady state voltages and currents will also be sinusoidal and of the same frequency. So in this particular case, we might have something which is our driving input over here. Any other voltage or current, or in this case some other voltage, is another sinusoid of the same frequency. But I need to find the B and the phi, because that can change. Certainly amplitudes and phases can change. So we need, when we say determine the solution, it involves working out what B and phi are, and that's what we've done once already at the start of this lecture. What are B and phi? They will typically depend on the frequency of operation of the circuit. I mentioned inductors and capacitors give us this frequency-dependent behaviour. That's what makes them so useful. Okay, so what's it used? Well, in many practical systems, the forcing function is a single frequency sinusoid, like at mains power, 240 hertz sinusoids, zooting around all over the place. But can we only analyse circuits with a single sinusoid then? Well, no. If we had two of different frequencies, we could use superposition. Get rid of one, analyse it with just one in there, get our solution. Get rid of the other, analyse it with just that one in there, and we can add up the final solutions at the end. Superposition allows us to do that. So if you had one 60 hertz sine wave and one 30 hertz sine wave in your circuit, you just get rid of the 30, analyse it for 60, then do the other way around and add up the two results at the end. So that's still useful. Finally, have you done any Fourier series? It turns out that any function you can think of, basically, I can make it up by a sum of sinusoids. And I can get more and more accurate approximations to functions by taking sums of sinusoids. A bit of this sinusoid at 10 hertz and some of this at 20 and some of this at 30 and some of this at 40. Put it together in the right way and I can make a square wave. Okay. It's called Fourier analysis. So once I've done that, I could take any input function, break it down into how it's represented or approximated by a sum of sinusoids, and then use superposition and our analysis here that we're going to do, and I could get the output to any input function. So this frequency domain analysis is a very useful thing that we use again and again and again. Just so you know, that's what we did on the first few slides today. But we did it for a special case where Vm was 1 and the resistor and inductor were also 1. Here is the more general case, but you can see the solution of an amplitude cos of omega t minus tan inverse something is exactly what we had before. Slightly more general version, but step through it and you'll see it's pretty much the same procedure we followed. Matching coefficients of sine and cosine and using trigonometric identities. But the point is there's an easier way. We can use complex numbers because a complex number has an amplitude and a phase. We use a complex number instead of a sinusoid. The amplitude of the complex number is the amplitude of the sinusoid. The phase of the complex number is the phase of the sinusoid. There's the direct matching between complex numbers and sinusoids. So instead of trigonometric identities and playing around with sinusoids, we can use complex numbers and complex arithmetic. This thing is, of course, critical, how we move between polar and rectangular forms. Euler's formula or Euler's equation. But there's one catch. I'll just let you read that. I had to blank something out there. It was a bit rude. Amazing result. E to the I pi equals minus 1. How good is that? Relating all these fundamental, deep mathematical quantities together in one equation. Beautiful. There's a catch. What do we use I for? So we better use something else for the imaginary number. So electrical engineers use J. Oh, I know. Freaky. J. J, not J for Jamie. J. Electrical engineers use J for imaginary numbers. It's the next one along in the alphabet. H-I-J. It is too. Look at that. So we won't use I in this unit, we will use J. It looks very natural to me, maybe weird to you. E to the J omega T equals cos omega T plus J sine omega T. That's actually real. That's not a J. We will use J for the square root of minus 1 so we don't get confused with current. So that's the setup. The next 2 lectures we'll see how to analyse circuits with lots of capacitors, inductors and sinusoidal sources. So that's where we're heading. I'll leave you with that. See you on Wednesday. Thanks for listening. I'd have a think about how you want to use the lectures in the last week too. So we don't have any new technical material for the last week. Do you want us to go over old exam papers or just not have lectures or have a think about it?